Welcome to the fastest way to learn data structures and algorithms with this premium revision material. Today, we are mastering LeetCode 433, Minimum Genetic Mutation. This is a classic shortest path problem that perfectly demonstrates the power of breadth-first search. Let's look at the problem. We are given a starting gene string and a target N gene. Each gene is 8 characters long, using only A, C, G, and T. We can change one character at a time, but there is a rule: every intermediate mutation must be registered in our genetic bank. Our goal? Find the absolute minimum number of mutations to reach the target. If it's impossible, we return -1. Think of it like a high-security laboratory vault. You have an 8-character access code. To reach the final clearance level, you can only change one character at a time. However, every new code you generate must be a valid, authorized sequence from the lab's central registry, the bank. If you try to use a code that isn't in the registry, the vault stays locked. We want to find the shortest sequence of authorized codes to reach our final destination. To solve this efficiently, we use breadth-first search, or BFS. Since every mutation costs exactly one step, BFS is the perfect tool to find the shortest path. We treat each gene string as a node in a graph, and a single character mutation as an edge connecting two nodes. Let's dive into the dry run. We start with our gene AACCGGTT and want to reach AACGGTA. Our bank contains 3 valid mutations. We also keep a visited set to avoid going in circles. Step 1, we place our starting gene in the queue with a mutation count of 0. Step 2, we pull AACCGGTT from the queue. We try changing each of its 8 characters to A, C, G, or T. Most of these aren't in our bank. But changing the last T to an A gives us AACCGGTA, which is in the bank. Step 3, we add AACCGGTA to our queue and mark it as visited. Our mutation count is now 1. Step 4, now we pull AACCGGTA from the queue. Again, we try all possible single character mutations. We find that changing the 3rd character from C to A gives us AACGGTA. Step 5, is AACGGTA in the bank? Yes. Is it our target? Yes. Since we reached the target using BFS, we know this path of length 2 is the shortest possible mutation sequence. Now, let's look at the Python implementation. We first convert our bank into a set for O of 1 lookups. We use a queue to store pairs of the current gene and its mutation distance. While the queue isn't empty, we pop the current gene. If it matches our target, we immediately return the distance. Otherwise, we iterate through all 8 positions, trying all 4 possible characters. If a new mutation is in the bank and hasn't been visited, we add it to the queue and the visited set. If we exhaust the queue without finding the target, we return -1. Looking at the complexity, the time complexity is O of B times L, where B is the number of genes in the bank and L is the length of each gene. This is because we process each gene in the bank at most once. The space complexity is also O of B times L to store the bank and the BFS queue. And that is minimum genetic mutation mastered. Save this video for your next interview, and follow Leo Academy for more premium DSA guides.